Hello, I'm Ellen Stofan, the John and Adrian Mars Director of the Smithsonian's National Air and Space Museum, speaking to you from my home office. Thank you for tuning in to tonight's Exploring Space lecture. Last month's lecture on black holes was a fascinating discussion, and I am looking forward to hearing from Dr. Michael Werner tonight. This year's Exploring Space series has celebrated the diversity of techniques we use to explore the universe, and tonight's lecture will celebrate a great observatory that retired earlier this year after a successful 16-year career, the Spitzer Space Telescope. Spitzer was the premier facility for infrared astronomy from space, and we are excited to hear from Spitzer Project Scientist Dr. Michael Werner about its innovations and discoveries. Before we get started, I'd like to acknowledge our sponsors who make the Exploring Space lecture series possible. Thank you to Aerojet Rocketdyne and the United Launch Alliance for their support of this program, especially as we adapt it to bring it into your homes tonight. Now I'd like to turn it over to Dr. David Dvorkin, Senior Curator of the History of Astronomy and Space Sciences, to introduce you to Dr. Michael Werner. David.
Hi, everybody. Tonight's Exploring Space lecture by Dr. Michael Werner will continue our look at telescopes and how they have allowed us to discover and study objects ranging from near-Earth asteroids to the most distant galaxies. The Spitzer Space Telescope, NASA's Great Observatory for the infrared exploration of the heavens, was retired in January 2020 after a highly successful 16-year career as the premier facility for infrared astronomy from space. Spitzer has made major contributions to our understanding of exoplanets. These are planets orbiting stars other than the Sun. Spitzer has also aided our appreciation of how stars form and how earliest galaxies form. Spitzer was originally built to last for a minimum of 2.5 years. But it lasted in the cold phase, that means in the phase where it was refrigerated, for over 5.5 years. Then on May 15th, 2009, the coolant was finally depleted and the Spitzer warm mission began, which still lasted over 10 years until it was retired earlier this year. Tonight's speaker, Dr. Michael Werner, is the project scientist for the Spitzer Space Telescope. And also, he's the chief scientist for astronomy and physics at the Jet Propulsion Laboratory of the California Institute of Technology in Pasadena, California. He's been an active researcher in infrared astronomy for over 40 years, studying star formation, the interstellar medium, and the central regions of our galaxy. He has served as Spitzer Project Scientist since 1984 and was one of the leaders of the evolution of Spitzer from originally being a shuttle-based payload to now the elegant free-flying observatory that has operated successfully in an Earth-trailing solar orbit for so many years. Dr. Werner was named the 2006 George Darwin Lecturer by the Royal Astronomical Society in recognition of the success of Spitzer. He's also the recipient of 2 NASA Outstanding Leadership Medals and also the NASA Distinguished Public Service Medal. He graduated from Haverford College in 1963 with a BA in physics and received a PhD in astronomy from Cornell University in 1968. So tonight, Dr. Werner will discuss his work on the Spitzer team and will feature many of the remarkable images and informative spectra returned by Spitzer and incorporated into the more than 8,500 refereed papers which cite Spitzer's results. He will show us how Spitzer is setting the stage for future NASA observatories, including the James Webb Space Telescope. So, Michael, take it away.
Worked with NASA at developing a concept called Great Observatories, which envisioned 4 powerful observatories in space operating together to study astrophysical phenomena. Those are illustrated in the middle of the frame on the right. At the bottom, you see the electromagnetic spectrum extending from the gamma ray to the infrared. Right where that yellow bar is the visible rainbow that our eyes are sensitive to. And you can see that it's only a small part of the entire spectrum, which we now use to study astrophysical phenomena. So if you start at the little rainbow there, the shortest wavelength, the highest energy radiation we can see with our eyes is the violet. And next to that comes the ultraviolet, which is studied by the Hubble Space Telescope. The X-ray are studied by what's now the Chandra telescope, and the Compton Gamma Ray Observatory studies gamma rays from celestial targets. Returning back to Hubble, Hubble does a little work in the infrared, which is just beyond the limit where our eye can see. And then moving further into the infrared is the domain of the Spitzer Space Telescope. Like these other observatories, Spitzer was named for a famous astronomer of the past, in this case, Lyman Spitzer, who was a visionary astronomer in the 1940s and 50s who foresaw the power of observatories in space for astrophysical exploration. And in my mind, the completion of the Great Observatories with the launch of Spitzer in 2003 was a major accomplishment, some 20 or more years in the making, which hasn't been adequately celebrated. So I'm celebrating it. You will find that each wavelength band provides unique perspectives on astrophysical studies, although in many cases the telescopes work together. What I'll be doing in my talk today is talking about what's uniquely possible in the infrared, explaining why infrared is different in some ways from visible astronomy, talking about the advantages of space for infrared telescopes, talk a bit about Spitzer so you can see how it explains those advantages, and then talk about our scientific results, and at the end, a very quick overview of future NASA programs in this arena. On the left is a picture of the Spitzer Space Telescope undergoing a test at Lockheed Martin in Sunnyvale. I'll be saying more about the design of Spitzer a little later on in my talk. So the reason that the infrared is of fundamental importance is because of the fact that all objects, regardless of what they're made of, radiate in wavelength bands which depend on their temperature. So the sun, which is very hot, radiates visible light, as you all know. But infrared radiation comes from cooler objects, which are more like room temperature or perhaps a bit warmer. And that's illustrated here by my friend Rusty, the dog. So at the bottom, there's a picture of Rusty in visible light, which is either light from the sun or scattered lamplight. If you turn off the lamp and come back at night, you can't see Spitzer, you can't see Rusty in visible light, but you can continue to see him in the infrared where he's radiating the heat of his body. The warmth of his body is producing this infrared radiation. And you can see from the temperature scale on the right that the radiation is most intense, his temperature effectively is highest when you're looking closest to the blood supplies, like into his mouth or his eyes. And since Rusty is a dog, he has a cold nose. And what's going on here is something that you are all very familiar with in this day and age. When you go into a doctor's office or a store and they take your temperature with something that looks like a gun, they're really just measuring the infrared radiation from your forehead. And that's a clue to your temperature. It's the exact same principle as we're seeing here with Rusty. So given the fact that something as relatively simple as a dog looks different in the infrared than the optical, we can expect that astronomical objects will as well. And the unique characteristics of infrared astronomy are summed up in our slogan, the old, the cold, and the dirty. The old alludes to the fact that's illustrated here. On the left is a visible wavelength image of a field of distant galaxies. On the right, we've added a Spitzer image in the infrared, and you see this string of red dots right in the middle of the picture, which is called the cluster of galaxies. These galaxies are so far away that it's taken 9 billion years for the light from them to come to us. And the reason we can see them in the infrared and not in the visible has to do with the expansion of the universe. I'll be talking more about that a little later. But in infrared, we can often see very old radiation, that's been traveling in space for a long, long time. Next comes the cold, and that alludes to the fact that you've already seen in connection with Rusty that the objects are too cool to radiate visible light, can nevertheless radiate quite strongly in the infrared. Here we have a picture of what's called the Helix Nebula. It's a planetary nebula in a system which is a cloud of dust and gas. It's been ejected by a sun-like star in the final stages of its evolution. Our own sun will do this at some time in the future. And on the right, we have the infrared picture. That red cloud comes from dust particles surrounding the remnant stellar core, which was left behind as the planetary nebula formed. That dust is heated by that remnant core to a temperature of maybe 100 centigrade degrees above absolute zero, not warm enough to produce any visible light, but more than warm enough to reduce light in the infrared. And finally, the dirty has to do with the fact that space, whether in our galaxy or in other galaxies, is filled with clouds of cosmic dust. And you can see in this picture of a region where stars are forming in our galaxy that there are lots of dust clouds in there, which are making the field dark. When we look at the infrared, you see stars emerging out of that gloom. We can see these in the infrared because of the fact that dust clouds are much more transparent at infrared wavelengths than they are at visible wavelengths. So the cosmic dust shields things at visible light, but allows us to see them in the infrared. Under other circumstances, the light from stars is absorbed by the dust, which is heated up to re-radiate in the infrared. So dust helps us in two ways by allowing us, infrared benefits from interstellar dust in two ways: by being able to peer into regions hidden from view at visible or ultraviolet light, and by the fact that dust will radiate the energy it absorbs in the infrared. Two other comments about this image which are worth making. One is that this is an infrared picture. It was taken at infrared wavelengths by Spitzer. None of what you're seeing here can you see with your eyes, but we render it as a visible light image so that we can talk about it. And finally, the red flash up at the upper left of this region is produced by emission from hydrocarbon molecules, which are abundant in space, and which we'll come back to hear a bit more about later on in the talk. So there are all these great things you can do in the infrared, and people have done them for years from ground-based telescopes like the Palomar 5-meter telescope. Those efforts have been very successful, but there are a couple of reasons why you really want to go into space to do infrared astronomy. One is when you're in space, you don't have to worry about the absorption from the atmosphere, and you get access to the entire infrared spectrum. The other, which is even more fundamental, is that from the ground, your sensitivity or ability to see things is limited by the infrared radiation, both from the atmosphere and from the telescope. They're at about the same temperature as Rusty, and like Rusty, they produce copious amounts of infrared radiation. If you go in the telescope into space with the telescope, which is cold, so it has no infrared radiation, there's no atmosphere, and the skies open up in an amazing way, and you can go into much higher levels of sensitivity, much fainter targets than you can from the ground. It's like the difference between night and day. If you want to do infrared astronomy at night, you go into space with the cold telescope. Now we can talk about the Spitzer Space Telescope, which is a cryogenic telescope in space, a cold telescope exploiting the advantages I just described. On the left, you see a picture of Spitzer. The vertical silver and black thing to the left is the solar panel. Behind it, that cylindrical structure holds the telescope. I'll just refer to it as the telescope. And underneath the telescope and the instruments are there as well. Underneath all of that is the spacecraft, which steers the telescope around and sends the data back to Earth. Now, the unique thing about Spitzer, one of the unique things, is that we're not orbiting the Earth, we're orbiting the sun. And the reason for that is we want to be really cold. The Earth is actually a substantial heat source. So by getting away from the Earth, we have substantial advantages in terms of remaining cold. And because of that, we can always keep the system oriented. So the solar panel is oriented towards the Earth. The black layer behind the telescope radiates in space and helps keeps things cold. So we're making heavy use of what's called radiative cooling. And because of that, as David said earlier, even when we ran out of our initial cryogen, which was needed to keep the instruments cold, we've continued in what's called the warm mission since 2009. We retired in 2020, earlier this year, right after our Sweet 16 party. And let me call your attention to the people in that image of Spitzer. Spitzer is large, but not huge. And that's why we have the motto at the top of the slide, though she be but little, she is fierce. Here are a few facts, vital statistics about Spitzer. 85 centimeter telescope, about the size of a hula hoop, covers a wide wavelength range for imaging. That's pictures and spectroscopy. That's diagnostic studies. We have large detector arrays, large for that era. Because of the advantage of being cold and in space, Spitzer is more sensitive than a 10-meter telescope on the ground, working in the same infrared bands. We had over 9,000 refereed papers, more than one per day over our 16-year lifetime. And very importantly, Spitzer lives on, even though we're not continuing to take data. All of the data from Spitzer, and indeed from other NASA observatories, is archived in a very user-friendly way. And people will continue to use Spitzer archival data for decades into the future. So let's talk about Spitzer science. First comes star formation and planetary systems. Star formation is occurring in our galaxy even today. Stars are forming near the sun, even though the galaxy itself is about 13 billion years old, and the sun is 4.5 billion years old. In our neighborhood, stars are forming in cold and dusty or dirty environments, such as shown here on the left. So stars form when a dense cloud of interstellar dust and gas, which is also quite cold, becomes unstable and collapses or starts collapsing under its own gravity. As it does that, it heats up and a stellar core is formed, and eventually the star dissipates that surrounding material and becomes visible. But throughout the early phases, it's best studied in the infrared because the dust is cold and the star is hidden. As material falls onto the star, not all of it can fall directly onto the star. Some of it goes into orbit around the star in what's called a protoplanetary disk, which is shown in the artist's conception on the right. And it's in a protoplanetary disk like this that planets will form. We know that our own solar system formed out of such a protoplanetary disk for two reasons. One is that if you look at the orbits of the planets in our solar system on the sky, they all lie more or less in the same plane, which is the plane of this protoplanetary disk. In addition, the planets all go around the sun in the same direction, which is the direction in which the disk was rotating as it was forming early in the life of the star. Well, as you probably know, the study of planets around other stars, exoplanets as we call them, is now one of the growth areas of astrophysical research, which sort of blossomed over the last 25 years into an exciting and vibrant field of research. We now know that most stars like the sun will have several planets orbiting them, but it's not easy to see a planet around a star like the sun. That's shown here, where to physical scale, you can see the sun and the Earth, which is much, much smaller. Fortunately, not quite so close, but looking at our solar system from outside, it would be difficult to detect the Earth in the glare of the sun. Although that type of technology is now being developed, most exoplanet work to date has been done by looking for the effects of the planet on the light from the star. And because there are so many exoplanets, they're so common, A number of them are in orbits which are edge on as we observe them with Spitzer. And these are the planets, we call them transiting planets, that Spitzer has studied in greatest detail. So here's a picture showing what the orbit of such a planet would look like. And what's plotted below is the infrared light from the combination of the star and the planet as observed by Spitzer. They can't be separated, so you see the light from both of them together. So if I trigger this simulation, you see that first thing that happens is the planet goes in front of the star and blocks the light from the star. That's called the transit. And the amount of light that's blocked depends on the size of the planet relative to the size of the star. If the size of the star is well known, you can figure out the size of the planet from the fraction of the star's light that's blocked. And Spitzer has done this, and other telescopes have done it. In many cases, Spitzer's greatest accomplishment in this area was what's shown here, the identification or showing that 7 Earth-sized planets orbit this one star, the faint red star TRAPPIST-1. This was done by a 20-year observatory from 20-day observation from Spitzer, which was possible in our solar orbit, and which sorted out complicated data and identified new planets. So we have these 7 Earth-sized planets orbiting the single star, and you can see from this artist conception done by Robert Hurt that close to the star, water vapor would be in the form of steam. Far from the star, water vapor would be in the form of ice. But in between, there's a region called the habitable zone, where water could be liquid on the surface of these planets, which is considered essential for the formation of life as we know it. And in fact, the 3rd, 4th, and 5th planets moving outward from the star all lie in the habitable zone. And these will be studied by future systems looking to see evidence of biogenic processes or biogenic materials on these potentially habitable planets. Going back to our orbit for a second, all transit planets will produce a transit by blocking the light from the planet. But what comes up next depends on whether or not the planet is big enough and warm enough to produce its own infrared radiation. If that happens, you've got a situation like this, where as the planet comes out of eclipse, the bright side of the planet, which is always facing the star due to tidal locking, comes more and more into view. And you see more and more infrared radiation from that bright surface until the planet goes behind the star and is eclipsed, and you don't see any infrared light from the planet at all. So let's play that one more time. Coming out of the transit, the starlit side of the planet becomes more and more visible, leading to this phase curve in which the infrared radiation grows with time. When the planet goes behind the star, you have an eclipse because you no longer see the infrared light from the planet. By measuring the depth of the eclipse, Spitzer made the first detections of infrared light from exoplanets. And the depth of the eclipse is a good indicator of the temperature of the planet, because you know the size from the transit and the depth of the eclipse depends on the temperature if you know the size of the planet. You know how much radiation you're no longer seeing. In addition, the phase curve tells you something about the temperature distribution on the surface, because more and more of the planet surface is coming into view as you go around that phase curve. And what that's been made it possible to do is shown in this next slide, which is a picture of the temperature distribution on the surface of one of these transiting planets, which was derived from a phase curve such as the one I just showed you. So what you see here is latitude and longitude on the surface of the planet. And you see that the brightest spot is not where those 2 arrows intersect, which would be what's called the substellar point, the point where it's always high noon, but a little bit displaced from that because the heat from the star that the planet absorbs is transported by its atmosphere around the surface of the planet in longitude before it's re-radiated. And in fact, what was determined from looking at this image is that there are winds on the surface of the planet in the atmosphere with velocities of about 10,000 miles per hour, which are redistributing the absorbed starlight across the surface of the planet. Now, if you think about this, this is quite amazing. I'm sitting here with a straight face and telling you something about the temperature distribution and the dynamical processes on the surface of a planet, which in fact has never been distinctly seen. The fact that we're able to do this is a testimony to the ingenuity of the many scientists who've made such great use of Spitzer. Now we'll move ahead and talk a little bit about galaxies and the distant universe. Galaxies are more complicated than stars. Galaxies are huge collections of stars like our own Milky Way. And this picture shows as a function of wavelength, which is a characteristic of the radiation from electromagnetic radiation, where cooler, longer wavelengths correspond to lower temperatures. You see the visible light, and that's reproduced here in this relative brightness distribution by what's called stars. The light from the stars leaks over into the range seen by Spitzer. Next comes a lot of jagged radiation from those hydrocarbon molecules I told you about. And then you see at the longer wavelengths, the lower temperatures, radiation from dust heated by starlight. And this is about what the light from our own galaxy would look like if we viewed it from a distant perspective. We'll keep an eye on this stellar hump. We'll be talking a bit more about it in just a second. Now, Spitzer has studied nearby galaxies, as is shown here. This is the so-called Whirlpool Nebula. And the visible light image on the left and the Spitzer image on the right are almost mirror images of one another. And that can be seen most clearly in the spur that's going up to that small satellite galaxy. You can see that in the visible light image, it's dark, where in the infrared image, it's bright, because the dust that's producing the obscuration on the left is re-radiating that light in the infrared as seen by Spitzer. You can also see that companion galaxy, it looks kind of chopped up and messy in visible light, but because of the overlying dust, which is obscuring it. But with Spitzer, we can look right through that dust and see the dense ball of stars, which characterizes that companion galaxy. So by studying these distant galaxies, we're learning, these nearby galaxies, we're learning how to understand distant galaxies seen by Spitzer. This galaxy is about 20 million light years away, which is real far away, of course, but nowhere near as far away as the more distant objects seen by Spitzer. And as we move out of the local neighborhood, Spitzer tends to see galaxies not as beautiful resolved structures like this, but more often as faint smudges in the images. The way this works is shown here with the expanding universe. So the expansion of the universe shifts or stretches the radiation from distant objects more and more towards the infrared. We describe this distance by the redshift we call Z, and the light is stretched by 1 plus Z in wavelength. It takes time for the light from a distant galaxy to reach us. So we look back in time and space, and we do this more and more in the infrared because we're looking further and further back. That's illustrated over here on the right, where you can see again, this is the same image I showed earlier, the cluster of galaxies, which is at a redshift of 1.24, which means the light we observe here in the infrared is stretched in wavelength by a factor of 2.25 from where it left these distant galaxies as visible light. And that's illustrated above more quantitatively, where we compare the relative brightness as a function of wavelength for the nearby galaxy in black with what you would see from a similar galaxy at a redshift of 2, where the wavelengths are shifted by a factor of 3. And you can see as you go to higher and higher redshifts, the amount of light in visible bands drops, while that in the infrared increases due to the redshift and the shape of this stellar bump on the left. And note that this is a scale in powers of 10. So we're talking about factors of almost 100 drop in visible light and increases in infrared light. So the gold standard for the study of the distant universe is the Hubble Deep Field, which is our first in-depth look at the distant early universe. This is the visible wavelength image of the Hubble Deep Field, which was done in 10 days of staring by the Hubble Space Telescope in a small patch of sky, much smaller than the size of the full moon. People tried mightily from the ground, as shown in the middle panel on the right, to see those distant galaxies in the bands that Spitzer works in. But only with Spitzer has it been possible to study the infrared counterparts of these telescopes in the Hubble Deep Field, which have been studied extensively, as shown in the lower set of images by Spitzer in many of our different infrared wavelength bands. Now, when we put together all of the results from Spitzer on distant galaxies, both in the Hubble Deep Field and elsewhere, we come up with this remarkable figure, which shows the growth of the stellar mass of the universe with cosmic time. On the left is the cosmic stellar mass. You can think of this as the number of stars in the universe. On the top, we have billions of years ago. So we're talking about looking back almost 13 billion years in this figure. The universe, the Big Bang, occurred about 13.7 billion years ago. We're looking close to the Big Bang, and the red points are the data from Spitzer. And you can see that over time, we see the number of stars in the universe grow because more and more of the fuel that stars are formed of is being incorporated into new generations of stars. This is a growth by a factor of about 1,000 from the most distant galaxies at a redshift of 8 to the nearby galaxies. The rate of star formation has dropped remarkably in recent epochs because of the fact that all the fuel has been used up. Finally, we come to the most distant galaxy known, which is at a redshift of 11, seen when the universe was only 3% of its present age. You get some idea of how remarkable this is. At the top, you see the wavelength as emitted by the galaxy, and at visible wavelengths, it's way over in the upper right. That's where the visible light emitted by this galaxy has ended up, way out in the infrared where Spitzer can see it. Whereas if we look at this galaxy now in visible light from our vantage point, we can't see it at all because visible wavelength light from these types of galaxies is absorbed by hydrogen in the interstellar medium. And you need the combination of Hubble and Spitzer to study this galaxy in detail with the red data points fit to the model that you can see there. Spitzer and Hubble show that this galaxy is surprisingly massive. It's much more massive than many nearby galaxies in the current day universe. And galaxies like this are important targets for the James Webb Space Telescope, NASA's next Great Observatory for infrared astronomy. So that brings me conveniently to the upcoming mission chart. On the left, we have the James Webb Space Telescope, which will be launched in 2021. It will unfold and self-assemble on orbit. It has a 6.5 meter aperture telescope, which is 50 times more powerful than Spitzer's. You can see the little people on the clean room floor. Those are regular sized people. Give you an idea of the scope of magnitude of James Webb. And James Webb will overlap the wavelength regions of Hubble and Spitzer and make great progress in the study of the astrophysical phenomena which Hubble and Spitzer have been studying. The upper right is SOFIA, an airborne observatory, a 3 meter telescope in a converted 747 aircraft, which provides access to parts of the spectrum which could not be studied from the ground because of absorption by water vapor, which stays close to the surface of the Earth. So playing in the stratosphere lies above much of that water vapor and gets a good look at the far infrared part of the spectrum. The lower left is the Nancy Grace Roman Space Telescope, recently named for a pioneering NASA astronomer. This will do a variety of scientific investigations when launched mid-decade. In particular, it will follow up on Spitzer's study of what are called gravitational microlensing planets, which I haven't been able to talk about. And on the right, a mission that I'm working on is called Spherix. It's much smaller than the Roman telescope or the James Webb telescope. It's what's called a mid-X or Explorer mission, which will obtain spectra over the entire sky at wavelengths from the red end of the visible spectrum out into the infrared, which Spitzer has studied. And we'll follow up on Spitzer's observations of protoplanetary disks and host stars, the planetary systems, as well as doing some very exciting cosmological work. So this brings me to the end of my talk. Thank you for your attention. I'm looking forward to your questions. And if you're interested in more details or more information about infrared astronomy in general, and Spitzer in particular, I refer you to the book that Peter Eisenhart and I have written. Peter's the tall guy with the beard. The book is called More Things in the Heavens, and it's published by Princeton University Press and available from Amazon. One of the things I'm most pleased about in the book is the epigraphs we have from everybody from Edmund Halley to Winston Churchill. So let me close with an epigraph from T.S. Eliot, which describes much of the motivation for the exploration that's such an intrinsic characteristic of humankind. Thank you all very much.
Well, thank you, Michael, for a wonderful talk. And to all of you watching on the YouTube channel, thank you for tuning in. And please, if you have a question for our speaker, please put that into the chat that we have posted there. My name is Matt Schindel. I'm a curator at the National Air and Space Museum, and I'll be moderating the Q&A this evening. So we have some questions here from our audience, and so I'm going to ask those to you, Michael, on behalf of them. So our first question here is, can you talk about your experience at Haverford College and how it guided your career in astronomy?
Yeah, Haverford, like other small colleges in the East, particularly had an observatory and an astronomy professor, and actually quite a tradition of turning out professional astronomers. And when I was an undergraduate, I was majoring in physics, but I was taking a course in the observatory, and I wandered through the library and picked up a book which was written by someone like Isaac Asimov or Fred Hoyle or George Gamow, one of the popularizers of astronomy in the 1960s. And it intrigued me. I read it, and that sort of set me off on a career in astronomy. I was able to go from there to work at the Naval Research Laboratory for a year, where I met Martin Harwood, who I mentioned earlier, who became my thesis advisor at Cornell. But Haverford was seminal in this experience. I had a great mentor there named Lewis Green, who, as I said earlier, was a mentor for many professional astronomers over the years.
Great. We also have a question about the Spitzer telescope itself. You mentioned that it's a cryogenic telescope, and folks are wondering how exactly it stays cool.
Well, it stays cool because in the orbit that we're in, you can see from the picture here that the solar panel on the right totally shades the telescope from the sunlight, which is coming in from the right. And any heat that gets through that solar panel is radiated away by the black surface of the telescope that you're seeing on the left. The telescope is connected to the spacecraft. The spacecraft has to be warm because it contains lots of electronics and stuff. But they're coupled together extremely weakly by low conductivity struts. You can see one of the struts. It's a triangular structure above the black panel in the spacecraft, and also by very thin and well heat sunk wires, which are conducting the electrical signals back and forth. At launch, we had a few hundred liters of liquid helium, which kept the instruments, which are within the telescope, cold. The telescope itself was warm on launch, cooled down by radiating its heat into space, and stayed cold because of the fact that no heat was allowed to reach it. It operated at a temperature of about 26 degrees above absolute zero, even after we ran out of our stored cryogen.
You mentioned the launch of the telescope. Can you tell us a little bit more about how Spitzer became sort of a free flyer? It was originally supposed to be a shuttle-based telescope, is that right?
That's a very good question, Matt. And I was present when that transformation occurred. It was triggered. Spitzer has been under study since 1971, actually. I joined the project in 1977. In 1983, we'd advanced to the point where we were soliciting membership in our science team. But 1983 is also the year that IRAS launched. IRAS was the first major cooled observatory in space, and it pushed Spitzer forward dramatically in two ways. One is that because it was cold and in space, it had unprecedented sensitivity and revealed unambiguously the wonders of infrared astronomy. In addition, it retired a lot of technical risks having to do with the performance of detectors in space and how liquid helium, the main cryogen, would perform in space. And it became very obvious, particularly since it was also clear that the shuttle, which was to carry Spitzer into space, was not a good place to do infrared astronomy, that we should switch over to become a free flyer. And that occurred actually quite rapidly. After the initial solicitation for instruments had been released, we all had to write an appendix about what we would do as a free flyer, and we never looked back.
Well, that leads into this next question pretty well then. When you think about the science that you originally planned to do with Spitzer, how did those plans change?
Well, we looked at this when we actually started the Spitzer project seriously, so to speak, around 1993, when we were really building the system. We put together four major science themes. The study of star formation, the study of planets, the study of active and nearby galaxies, and the study of the distant universe. These have all been pillars of the Spitzer science program. But of course, we had no idea when we were doing this how abundant and exciting exoplanets would be. None were known at the time we started this. And we had no idea that we would be able to look as far back in space and time as we've been able to do with Spitzer, as I was describing earlier. So I think that for the most part, the broad scientific areas were defined before we actually launched, but the level of excitement, precision, and understanding that we were able to achieve in them was totally unexpected. And of course, there have been new wrinkles as well. The discovery of buckyballs in space was unexpected and very exciting. The fact that we're studying gravitational lensing was totally unexpected. And a project like Spitzer, most of the science is done by people who had nothing to do with building the telescope. And the full ingenuity and imagination of the science community has driven our science program forward.
I just want to ask you a follow-up question, because I think a lot of our viewers might not know what that means, that when you said that you've discovered buckyballs in space. Can you go into a little more detail about that?
Sure. Buckyballs are they're a type of a molecule which is shaped like a soccer ball and which is composed of 60 carbon atoms. They're called buckyballs because they're ball-like, they're round, and because they're similar in geometry to what's called the geodesic dome, which was a futuristic structure put forward by the futuristic architect Buckminster Fuller. So interestingly enough, buckyballs have been known in the laboratory for many years. They were first synthesized by a man named Harry Kroto and his colleagues, who were trying to study molecules in space, and they were looking to synthesize things that might be present in space. They came up with these buckyballs, and then 20 years later, we actually found them with Spitzer.
Mhm. So we have a question here, which is, what's the most surprising discovery for you from Spitzer? But it sounds like maybe this might be one of them.
Well, I think the TRAPPIST system with its 7
Mhm.
Earth-like planets is unprecedented and unpredictable. Okay, so that's certainly one really surprising discovery. I think the second one, which I alluded to during my talk, was the ability to map out the development of stars and galaxies over cosmic time in a way which, again, was totally unexpected to me. And I think a third area which has been very productive scientifically is to draw parallels between processes in our own solar system, both dynamical processes, composition, materials, and so forth, and what we now see going on in exoplanetary systems as well. There's an awful lot of similarities between the two classes of systems, which has allowed insights obtained from the study of our own solar system to be brought to bear on the study of exoplanet systems and vice versa.
Mhm. We have a question about communication with the telescope. How long does it take to transfer data from the telescope back to Earth?
Well, right now, when we stopped taking data in the end of January, we were about 20 light minutes away. So it would take 20 minutes for a signal from Earth to get to the planet, to Spitzer rather, and another 20 minutes for the data to come back to Earth. And so we finessed a little bit about this by starting the communication both uplink and downlink before a two-way link had been established, because that would take too much time. We were getting to the point in our orbit where the ability to send the data back over the vast distances was a challenge to our data rate and power capability on board, and it was just starting to eat into our scientific efficiency.
So we have a question here that I think must be from someone who knows their history of astronomy. It says, using the latest observations from Spitzer, has Viktor Safronov's initial theories on protoplanetary disks and accretion been proven accurate? Has he been proven right?
I'm not that familiar with Safronov's theories, although I'm vaguely aware of them because there was an astronomer at the Ames Research Center that I worked with on CERTIF, which as it was then called back in the early days. I think that Safronov would certainly have predicted the kind of protoplanetary disks that we've seen with Spitzer and other telescopes and studied in detail with Spitzer. So I think that part of the scenario, if I have my science right, which I might not, is probably pretty well borne out by what we've seen with Spitzer.
And we have a question about what ultimately happens to the telescope at the end of its life. Is there any point, or is it not cost effective, they ask, to recover the telescope or parts of the telescope, or is it sort of out there on its own for the rest of its life?
Well, of course, it's going around the solar system, so around the Earth's orbit, getting further from the Earth every year. Eventually, it will come back to be quite close to the Earth. When we retired Spitzer, we put it into a deterministic mode, which is called safe mode. So we know what it's doing. We know about where it is. We could reopen communications with it in principle, but in practice, that would be very, very difficult because the infrastructure on the ground that's required to do that is being retired as well. There'd be no particular benefit to retrieving the pieces from space, although it would be fun. I don't think it's likely to happen.
So now we have a question about the Webb Space Telescope. They're asking, what lessons should Webb learn from the Spitzer experience, or where can it pick up where Spitzer ended, perhaps?
Well, I think just to hark back to my talk for a second, that very distant galaxy that I showed. In fact, let's go back to that that chart, which was let me see, where is it? Okay. Okay, it's chart number 21, Giuliano. You can see this spectrum predicted by the gray line there is a prediction of what we would see if we were able to look at this distant galaxy with a powerful telescope that could chop the light up into fine bits and get what's called a spectrum. This is a primo target for the James Webb Space Telescope right out of the box, so to speak. It can start studying these kinds of galaxies to see whether our detailed understanding of what these young galaxies look like is on target or not. All we fit so far is the broad overall radiation, but not any detail as a function of wavelength. I think James Webb will also build on Spitzer's observations of exoplanets, because we developed specialized observing techniques and software to analyze the data from exoplanets, where we're often looking at signals as faint as, or precision as high as 1 part in 10 to the fourth. And I think the way we've done that with Spitzer will inform how it's done with James Webb. So those would be a couple of very explicit examples of how Spitzer will be setting the scientific stage for James Webb. We also set the technical stage for James Webb because they make extensive use of radiative cooling. And I'm confident that the success of Spitzer's radiative cooling was a big risk, retired a lot of risk, avoided a lot of risk that they might otherwise have to confront if they were uncertain about how well radiative cooling could really work.
Yeah. Well, we have time for just one last question, and I wanted to ask you a question based on something you said to me before the talk of sort of what you find most meaningful and most inspirational about this mission, sort of on a personal level.
Well, first of all, what I'd like to say, Matt, is it's been a pleasure to be here. I want to point out that thousands of people worked on Spitzer. It wasn't just me, of course, or me and my best friends. It was a large group of people who contributed in many, many ways. Their contributions are remarkable. And not only the people themselves, but their families. Building a telescope like Spitzer is not a 5-day a week, 8-hour day job. It required a lot of sacrifices on the part of the families of these workers, not the least of which was the sacrifice of my late wife, Edwina, and I want to dedicate this talk to her. If I go back a bit and look at how wonderfully Spitzer has engineered, how well it's worked, how flawlessly it's performed over the years, I realize that Spitzer is an example of the best that human beings can do. It shows what a group of dedicated and bright people, sufficiently supported and well empowered, are capable of doing. It's an example of the best that human beings are capable of, and the same is true for many other NASA projects as well. And I think it's important to keep this in mind as a sort of a goal and an inspiration in our troubled time of today. So I view Spitzer not only as a great scientific venture, but as a beacon pointing out what human beings are capable of, and something we can all bear in mind as we go forward.
Well, that's a wonderful note to end on. And I want to thank you again, Michael, for a wonderful talk. I want to thank our audience for tuning in on our YouTube channel. And I also want to thank our sponsors one last time, Aerojet Rocketdyne and United Launch Alliance, for their support. So thank you all at home from the National Air and Space Museum. Good night.